my name's Justin Sulik, and I'm going to be talking about how the freedom to fail can unleash the benefits of cognitive diversity. So we know that cognitive diversity offers epistemic benefits. For instance, it makes for better science. If we have a wider range of interests, knowledge bases, skills, values, we're likely to tackle a wider range of scientific questions and make a wider range of scientific discoveries. So what more do we need to know? Well, the problem is that there are plenty of arguments that cognitive diversity also has costs. For instance, if you have wildly different perspectives, it may be harder for you to agree on anything. So even granting that cognitive diversity promotes epistemic benefits, we still need progress on just when or how it does so. This can include looking at what kinds of cognitive diversity are beneficial, and it also includes paying attention to group dynamics. So for instance, what's best for the individual scientist isn't the same as what's best for science. So today I'm going to be focusing on one kind of diversity in learning strategies, and I'm going to be looking at group dynamics in the context of an epistemic landscape model. So by social learning strategies, I mean this. If you have an individual learning strategy, you are going to be learning from first-hand experience, from direct contact with the world. An extreme example of this is a maverick. If you have a social learning strategy, on the other hand, you're learning from others who themselves may have had first-hand experience of the world. And an extreme version of this is a conformist. So the question is a mixture of strategies useful for doing science? I'm going to be looking at group dynamics with a variety of learning strategies in the context of an epistemic landscape model. Now, this kind of model situates a research question within a landscape such as this one. The position on the landscape, the XY position, references different approaches, theories, or methods used to answer a question. And the height of the landscape at each point represents the epistemic value of that approach or theory or method. How much have we learned from following it? Typically there are a couple of peaks, so points or approaches or theories that offer outstanding epistemic value, the great scientific discoveries in this field. And then there's also the desert, which offers epistemic value, but it is certainly not the optimal level of epistemic value. And typically simulated agents begin in the desert, and their aim is to discover all of the peaks. But I'm going to be looking at a slightly more updated take on this kind of model by Pohjonen, where the aim is to excavate as much epistemic mass as possible. In other words, it's not enough to just visit the spots, the peaks. You have to do work when you get there, literally by depleting the amount of mass at that point in the landscape. And in this model, learning strategies are implemented as follows. So there are a bunch of agents, and they start out by doing local hill climbing, basically trying to head uphill as much as possible. But once they've headed along their trajectory and reach a local maximum, going further along that heading would take them downhill. So at that point, they stop and they poll others. In other words, they have a look where other people are. Now, each agent has a vision cone, a 3D cone defined by the slope, how steep or how shallow that cone is. And each agent is able to see any others within that cone. They're able to see where those others are, what approach they're using, and they're able to see how high others are, the epistemic value of their approach. So for instance, a bunch of agents might not be able to see anyone else, but this agent here at a lower point in the landscape, for instance, is able to see two other agents. They fall within its vision cone. And at that point, a decision procedure kicks in, so the red agent is going to identify the other agent that offers them the maximum gain for the least amount of difference. So this, like pretty much everything else I'm going to be talking about, involves a slope. They're trying to find the steepest slope for epistemic benefit. In this context, a maverick strategy involves having a narrow cone or a very steep slope, a very high threshold. So this agent is not likely to want to learn from anyone unless they're extremely close and they're on an extremely high peak. Whereas this agent is more of a conformist. They're willing to learn from anyone who is even slightly higher they are, even if that they are quite far away. So, does diversity of learning strategies benefit the group? Previous work suggests that yes. In particular, having a small number of mavericks can benefit the group, even if the mavericks themselves individually don't always do so well. But one problem is that these studies have relied on categorically distinct learning strategies. In other words, contrasting mavericks with conformists. And realistically, people are more variable in their learning styles. There are very few extreme mavericks, people who are completely unwilling to pay any attention whatsoever to what anyone else is doing. We may be more or less maverick and more or less conformist. But if we introduce this idea of continuous learning strategies, this raises a question. If it turns out for a particular group, say, that the optimal diversity is 8 conformists and 2 mavericks, so 8 people with threshold 0 on an arbitrary unit scale and 2 people with a threshold of 1, does their success reflect their heterogeneity? Or might it just reflect their average threshold, which in this case is 0.2? If so, an homogeneous group of 10 agents who all have a threshold of 0.2 might do just as well, and in that case we might be finding a benefit of moderate non-conformity rather than a benefit of diversity per se. So in trying to probe this issue, I'm going to be using similar epistemic landscape models. One important parameter is going to be noise. You can see that the landscape on the right is noisier than the landscape on the left. And this basically just represents problem complexity or problem difficulty. Now, in 2 separate conditions, one is the homogeneous condition. In the homogeneous condition, for each run I will select a slope from the range from 0.1 to 0.9 and set all agents in the population to have their social learning threshold as that slope. So for instance, if the slope is selected to be 0.1, I'll have a group of conformists. If the slope is 0.9, I'll have a group of mavericks. On the other hand, in the heterogeneous condition, instead of setting all agents to have a particular slope, so let's say 0.3 is selected for this run, instead of everyone having 0.3 as their social learning threshold, I'm going to draw a random selection of slopes from a distribution whose mean happens to be 0.3. So the overall average will be the same, but the range of values will be different. And this is just to illustrate how it looks. In a homogeneous run, for instance, the conformists here are very quickly converging on one of the peaks, and then they're very efficiently depleting that peak, gaining as much epistemic value from that approach as they can. But once they've done that, once they've depleted that peak, they tend to stick together because they're conformists and they don't really explore the landscape very much. So they don't discover the other peak. There is only one other peak on this landscape, I should say. This is a toroidal surface, so the thing that looks like 4 peaks here are in fact 1 because this wraps around on all sides. On the other hand, with a group of homogeneous mavericks, they stay rather spread out on the landscape so that they're quite likely to discover both peaks. You can see that there are agents here and here in the middle, but they are doing work there rather inefficiently. It would take them quite a lot of time to excavate the epistemic value from those positions. On the other hand, with a heterogeneous population, some mavericks and some conformists, both peaks get discovered quite quickly, but then the other agents will flock there and help excavate those peaks quite efficiently. So by the end of the run, all of the epistemic mass on this landscape has been depleted. We have made all the discoveries we can make. So overall, this is what the averages look like. Here on the X, I'm showing you the time steps throughout the simulation. On the Y-axis is the proportion of work, of scientific work that's been done, the amount of discoveries that have been made. And when noise is at its lowest setting, when there's very little noise in the landscape, there is no effective social threshold, and that's because in this situation, any signal that someone is higher than you is an unambiguous signal as to where the peaks are, so it is worth following those people. When there's a bit of noise, though, and things are a little bit more ambiguous, then there is a benefit to have a higher social learning threshold. So the conformist populations tend to discover one peak but not really get much further, whereas if they're a little bit more independent, they'll discover both peaks over the run of the simulation. But the interesting thing is that the heterogeneous groups and the homogeneous groups are exactly the same. There is no benefit to diversity, in other words, in this setup so far. There's just a benefit to moderate non-conformity. And the same thing happens for higher levels of noise. So what I'm adding to these simulations next is a freedom to fail parameter. So previously, agents would do local hill climbing, and then when they start heading downhill again, when they've reached a local maximum, that's when social learning kicks in and they poll others. Instead now, I'm adding a failure parameter, whereby they will tolerate a certain amount of downhill if that's within their failure threshold. So, for instance, if it's within this agent's threshold, they will continue along their original heading and potentially discover a higher peak. So everything is the same as for the previous simulation, except I'm setting tolerance to failure for each run to 0, 0.2, or 0.4. That just represents how much of a downhill slope they will allow, and therefore 0 is exactly what we have just seen, that their social learning will kick in the minute people start going downhill. And I'm focusing on the medium noise setting here because that's where things get really interesting. For the homogeneous populations, there is no effective tolerance to failure. We see the same benefit of social learning threshold as we had previously, such that conformists do less well overall and more independent groups do better. On the other hand, for heterogeneous groups, when the tolerance to failure is 0, as we had in the first set of simulations, this point is the same as for the homogeneous group, but with increasing tolerance to failure, we see now a benefit to diversity, especially for these groups that are slightly more on the conformist side. So there is a benefit for diversity for more conformist groups. So, in the first simulation, we saw that noise is necessary for non-conformity to be beneficial. We saw that without any freedom to fail, what matters is the mean threshold, the mean level of conformity, not the diversity of strategies within a group. But with some freedom to fail, diversity can benefit the group if the group is moderately conformist. And this is interesting because humans are prone to social learning. Social learning is one of our major strengths. In future work, one thing I would like to look at is try and unpack what freedom to fail really means here. So for instance, you could imagine this in terms of incentives. Maybe the rewards shouldn't be tied to your current level of epistemic value in the landscape. We could imagine it in terms of perspectives. Maybe mavericks gauge the epistemic value of their current approach slightly differently from everyone else. And we could also think of this in terms of motivation. So maybe mavericks find novelty intrinsically rewarding, in which case they don't mind taking a slight decrease in epistemic value because they will gain a lot of value from the novelty of the new position. Thank you very much.